Next lesson, we're going to look at titrations. We're going to carry one out. Titrations are a volumetric, that means using volumes, method of working out the concentration of an unknown compound based on the concentration of something that is known to react with it in a controlled way. We're going to look at acid-base titrations. That's using acid and alkalis like we've done before, but in a controlled manner. Before we get to that, we need to talk a bit about pH. Remember, we have our pH scale, which runs from 0 through 7 to 14. And at 7, we're neutral. That's our water, things like that. At 0, we're all the way into the strongest possible acids. And at 14, we're in alkalis and bases. So we can use this. This tells us useful information. When we completely react an acid with an alkali, we will get to neutral if we've done it precisely. That's what our titration is going to look for. We're going to see how much acid will make an alkali neutral. In order to do this, we need to be able to measure it. Now, we could use a pH probe or meter, which is an electronic device. We might have time to do that. But what we're going to do is we're going to do it with an indicator. Now, you might have come across a universal indicator. In fact, I really hope you have come across a universal indicator. We have used it a fair amount. And that goes from red for an acid through oranges and things like that for weaker acids, through to green at neutral. And then out the other side, we're looking at things like purple and blue in here. So it's a really useful mixture of indicators. It tells us a whole load of information with one test. Put a drop in, test it on some paper, we'll get this nice range. But it's not very good for a titration. Because it's got this range of colours, it doesn't give us what we call a specific endpoint. It doesn't show a nice clear colour change. We need something better. We have two options. We can either use litmus, which has two colours. In acid, litmus is red. And in alkali, litmus is blue. So that's nice and clear. It's got a very sharp colour change between those two. The other option is a bit of a mouthful. It's phenol phthalate. And yes, that is spelt PHTH right there. That's a th sound. Phenolphthalein is a bit different. It doesn't have two colours really. In alkali, I don't have a good pink, but it's pink. And in acid, it's colourless. So we've got two options. Phenolphthalein is really good because it's a really clear colour. Going from colourless to pink or pink to colourless is really easy to spot. So we tend to use phenolphthalein quite a lot in school. So that's our acid and alkalis. That tells us what we're looking for. Well, we need to look a little bit more deeply at what's going on in this reaction between an acid and alkali. And we can do that by looking at something called a pH curve. A pH curve is just a type of graph. And it's made by plotting the changes in pH that happen as we go through a reaction. So up the y-axis we'll put the pH, and along the bottom we're going to have the concentration. Now let's say we're going to have the concentration of the acid down here. So we'll start up here with a really strong alkali. Now to start with, adding the acid doesn't have very much effect, so it's fairly flat for quite a while. Then the acid starts having a dent on the alkalinity and it starts dropping, and it drops in the perfect world really quickly as it neutralizes that alkali, and we come out the other side and we just have all acid. And it's this point, should be halfway down there, that's our pH 7, and that's our neutralizing point. That's what we're going to do. So if you were asked to sketch one of these, which is something you could be asked to do in an exam, you need to know starting pH, you'll need to know your end point volume. That is where you get to 7, and you need the pH range over which this change happens. You need the range. That tells you how big a place you need for the slope of your graph. It should always be quite narrow. And we can only really see this with our single indicators, not with our universal indicator, something like that. And we could measure this with a pH probe. Hopefully I'll be able to demonstrate this to you. We don't have many probes in the department and they are quite fragile, so we can't do this as a whole practical, I think. So that's what's going on in the background of the reaction. Here's what we're actually going to do. We're going to have our alkali with an unknown concentration, and we've got our acid which is known concentration. And what we're going to do, we're going to take our alkali, we're going to measure using a volumetric pipette, not a squeezy pipette, a volumetric pipette. And they look like this. They're sort of a glass straw with a bulb in the middle. These are very precise pieces of glassware. Because of that they're quite expensive and fragile. They're marked with their volume. We mostly use 25 centimetres cubed in here. And they have a little tiny mark. That's where you're filling to. And to fill them, we're going to use a pipette filler. The pipette fillers we have in school look a bit like a syringe with a dial on the side, and they're a syringe, they've got a plunger in the top. They've also got a little switchy thing on the side. This switch lets air in so that you can let out little bits of the liquid you're measuring. What you do, close down the plunger, and then this rubber end will slot carefully over here. You turn that lifts up the syringe plunger and sucks the liquid in. You can press this switch and push the syringe tube back in if you need to add some more liquid. You can also just put your thumb over the end once you've filled it. I recommend fill it beyond the line, take the filler off, get your thumb over the end really quickly. You can just sort of rock your thumb and that will let the liquid down until it reaches that. And remember, when you're measuring liquids, you've got the line in there, and if you're measuring water, you want the meniscus, the lower point of the curve, to just be on that line. So that is the most accurate way of doing this. So we've measured out our accurate 25 centimetres cubed into here, so we know exactly the volume. Then in our burette, which is just a long glass tube marked off in centimetres cubed with a useful little tap on the end and a very fine nozzle, we're going to put our acid. Got our indicator in here already, so as we add drops of acid in, keep swirling this to mix it, and as soon as this changes, so we get a little bit of pink, that stays there after you've swirled it, that is your end point. Now you reset it all again. If you've used less than half of your burette, you can start from the volume you started from before and do it again, otherwise you'll have to fill it up again. I'll tell you about filling burettes in school. We're going to do that at least 3 times. We need to get concordant results. And ideally, that means we're within about 0.1, we can be that precise, centimetres cubed for each of our results. Concordant results means we've got a nice reliable titration. Once we've got that, we can take an average and start to do our calculations. So, we're looking to work out the concentration. Remember, our concentration equation is concentration is moles divided by volume. And remember that we need our volume in decimeters cubed. So centimeters cubed divided by 1,000. And we're looking for the moles of sodium hydroxide. So, what do we know first? Well, we know the acid. And we know the concentration of the acid, we know a volume, so we can work out moles equals concentration times volume. And in your case, it will always be a 1-to-1 ratio. So the moles of acid equals the moles of alkali. You can work this out by using the equation, but you don't need to. If you have the chemical equation, you can show that, but it will always be 1-to-1 for you guys. Moles of acid equals moles of alkali. So moles of alkali with a known volume, because we measured that earlier, remember, will give us our concentration. And that is what we're looking for. I'll be asking you to work through this as one of the questions that I've set you for your homework. Don't forget you can go back and watch this again and again if you need to step through the procedure. You're working out the moles of your acid, concentration times volume, which tells you the moles of alkali, which means you can work out the concentration of your alkali. So it's a 2-step process once you've done your titration. And hopefully this will agree with the concentration that we have actually used. So what have we covered? We've covered pH curves, we've covered actual pH scale, measuring pH, remember you can use universal indicator, specific indicators, pH meters. We talked about sketching pH curves. You can read off those pH curves as well, that's graph work. And we've talked about how to use the burette and the pipette a little bit. Remember, always use that pipette filler. I've never seen anyone do it, but the risk is you could use it like a straw, and that you've got glass on the end of it, on the end of your little pipette. This is a whole glass thing. If this has got smashed, you're going to get sharp bits there. And if you just suck up your sodium hydroxide into your mouth, that's bad as well. So always use a pipette filler. And that's it. That's what you need to know for C5d titrations.